Thank you all for joining us for our SICSS-Howard Mathematica Lunchtime Talk. During these chats while you chew, you'll meet interesting people or organizations that are doing cool and complementary work to what you're currently learning about in the Summer Institute at Howard University. If you don't have your lunch yet, hit pause. For those of you with food and beverage in hand, let's get started. I'm proud to introduce one of our SICSS-Howard Mathematica alums who will introduce our speaker.
Thanks, Nanette. My name is Erica Kimigoto, and I am a research scientist at University of Arizona, and I am also a recent PhD graduated from the Department of Geography from the University of California, Santa Barbara, and my research is in the field of risk and disaster. I am a SICSS-Howard Mathematica 2022 grad, and I am honored to introduce Sara del Valle, Ph.D. from Los Alamos National Laboratory.
Hello, everybody. My name is Sara del Valle. Thank you so much for the opportunity to chat with you today and talk about my research. I am really honored to be here, and I am excited also to get to interact with you in the Q&A. So thanks again. Today, I'm going to be talking about some of the work that we do at Los Alamos National Lab on disease modeling and forecasting. But before I start my presentation, I kind of wanted to go back and give you a really, really short introduction about my career journey. And so let's see, there you go. So I just wanted to give you kind of a brief overview of where I come from, my roots, and where I am. I was born in Mexico. My parents are pastors of an evangelical church, and that was always kind of interesting growing up in Mexico, where the majority of the population are Catholics. We moved to the US when I was 16 because my dad was given a church in Brooklyn, New York. It was a Spanish-speaking congregation in Brooklyn, and they asked my dad to come to the US and bring his family. So I moved to New Jersey when I was 16. And I finished high school in New Jersey. When I finished high school, I didn't really know, I was new to the college kind of work and an area. And I'm actually a first generation college graduate. And I relied a lot on my mentors in high school and advisors about where I should go. So I ended up going to NJIT, which is the New Jersey Institute of Technology, where I majored in applied mathematics. During the summer, I used to work as a math tutor for several summer internships within NJIT, but one of my advisors suggested going to an REU program, which is a research institute for undergraduates. I applied to several, but I ended up choosing to go to Cornell University. And that's where my life basically changed. I found epidemiology, which is an area of how you can use apply mathematics and use them to study epidemics. And so after my summer internship at Cornell as part of the REU program, I decided that I wanted to pursue a PhD. And so I met my advisor during the REU. He was actually from the University of Iowa, but he was helping with the summer program at Cornell. And so I ended up going to the University of Iowa. And I continue majoring in applied mathematics and computational sciences, but all my applications were on infectious disease modeling. And then as I was just finishing my coursework, I got the opportunity to come to Los Alamos as an intern. I was supposed to just be here for a year, but that was in 2003, and I never went back. And so I've been here at Los Alamos for 20 years, and I think it was the best decision that I made. And the reason why I ended up here was because the director from the RU program at Cornell got a position at Los Alamos. His name is Carlos Castillo Chavez. And so he invited me to come with him and his students and spend a year here in Los Alamos. And And the reason why I mentioned this is about the power of connections. There is so much value in creating networks. You never know where they're going to lead you, so take advantage of that. And so that's my career journey in a nutshell. Okay, so just a little bit about Los Alamos in case many of you don't know. So we're a government research institution. Most people probably that come here to talk to you are from academic institutions. And so that's why I like to just give a really brief introduction about Los Alamos. We focus on solving national security issues. We are in New Mexico, and there's a map right there and showing where Los Alamos is. And if you've ever watched Breaking Bad, you probably are familiar with New Mexico. We were established in 1943, and initially it was organized during the World War II for the design of nuclear weapons. But since then, they have diversified the portfolio, not just focusing on weapons, but now there's a lot of work on engineering, physical sciences, earth sciences, simulation and computation. And specifically, I work on infectious disease modeling. And we have about 14,000 employees, including students and postdocs. And I always also just like to give a shout out about some of the opportunities that we have here for undergraduate and graduate positions, postdocs, and lots of summer schools and internships. So if you're ever interested in a summer internship or in a graduate position or a postdoc position, just feel free to reach out to me. Okay, so now I'm going to start about and give you a really brief overview about my work. And this is from a clip from National Geographic. Our work was featured in the show The Big Picture with Kyle Penn. And here they just kind of talk about what we do. And so I think it will be a good introduction before I kind of go into my work. But nowadays, infectious diseases are a national security issue.
Sara del Valle is part of the first line of defense against what could be the next global pandemic.
You can clearly see how it starts at airports, Chicago, Atlanta.
At Los Alamos, they run what-if computer simulations that predict how far and fast the fallout from a biological weapon might spread, and how many people might die.
We need to figure out how to quickly distribute vaccines and treatment. After the anthrax release in 2001, there was a concern that other diseases could potentially be spread, and so that's why we started developing these systems that could allow us to understand what-if scenarios.
What-if scenarios can be terrifying and ominous.
And so prior to the pandemic, I think people didn't really understand a lot of the work, the research that went behind infectious diseases. But one of the silver linings of the pandemic is that it highlighted the role that scientists and researchers have on combating many different hazards and such as infectious diseases. And so while many people think that, the COVID-19 pandemic was one of the first pandemics, there's been many, many pandemics throughout history. And as long as humans have lived on Earth, we have coexisted with many, many infectious diseases. And here I'm just kind of showing you a graphic that shows the impact of many pandemics and the millions of people that have died as a result of these pandemics. And so the goal of my team is to improve decision support. And so we use many different data streams, mathematical and computation models, and we try to quantify uncertainty. And so I'm kind of going to start high level and kind of introducing you some of the tools that we use, and then I'm going to build from there. So mathematical modeling for infectious diseases has been a very established area. And so I'm kind of going to start from the beginning, and there's evidence of epidemic modeling in the 1500s with John Grant, and doing very kind of simple comparative risk and assessments of different causes of death. Then there's a lot of work by Bernoulli on mathematical models as he was studying the inoculation of smallpox. Lots of work in the 1800s by John Snow, especially as it relates to cholera. And so he basically, there was an outbreak of cholera in London, and they didn't really know what the cause of it was. And so John Snow was able to pinpoint the issue as there was a pump in the middle of the city, and that water pump was actually providing contaminated water to many people in the neighborhoods. And so he was able to pinpoint that and use kind of like the special analysis to help them identify the cause. And as you kind of moved towards the end of the 1800s, there's also more evidence of mathematical modeling. And then finally in the 1900s, there's a series of papers by Kermack and McKendrick that basically gave birth to a lot of the mathematical epidemiology tools that we currently use. And so it basically described how we could model infectious disease transmission in communicable diseases. And so this is the simplest model that we use, and probably many of you have seen this type of modeling during the pandemic, and it's called the Susceptible Infectious Recover Model, or SIR. And the way this works is basically you break the population into 3 compartments. So you have susceptible people, you have infectious people, and then you have recovered people. And then you have some rates at which people move from one compartment to the next one. And so in this case, I have lambda representing the rate at which people move from the susceptible population to the infectious population. And then the way which people would be moving across those 2 compartments depends on obviously the number of contacts, how transmissible the virus may be, and also contacts with infectious individuals. And then you can describe this movement with a system of differential equations. And then you can study the spread of epidemics in a small population or a hypothetical population. One thing that I like to mention about this is, when I was in high school and I was starting to learn differential equations, I remember thinking like, there's no way anyone uses differential equations in the real world but now I use differential equations on a regular basis to study epidemics. So this is just to highlight that sometimes we don't see the mapping and the applications of what we're learning, but it's very important. And so then if you initialize the system of differential equations with some parameters, then you will get something like this, this figure showing in red, I have the susceptible population, the infectious population. In black is the susceptible population, and then in blue is the recovered population. And so you can kind of see how the susceptible declines as a function of time, the infected population increases, and then finally everybody kind of recovers at the end of this simulated piece. But one of the main issues with this type of modeling and tool is an assumption about homogeneous mixing. So when you break the population into 3 boxes or 3 compartments, you are assuming that everyone in the susceptible compartment have an equal chance of getting infected. And so I am showing you here in a kind of cartoon representation. So imagine each of these nodes are people. The green ones are susceptible people. The red ones are infected. And then the purple ones are recovered. And so we are not all connected with each other, right? In our communities, we interact with our friends or our classmates or our coworkers, our families. And so this assumption that everyone is connected will give you an overestimate of what would happen if you simulate an infectious disease spreading in a community. And so what happens with these SIR type models is that at the end of an epidemic, for the most part, you get everyone infected. And so here I'm showing you a network representation of people at time 1, and then the next one is at time 2, and you can see how the disease is going to spread really quickly. And so What we need in our models is, in order to have more realistic representations of what happens in the real world, is heterogeneous mixing assumptions. And so here I'm showing you what would happen in a heterogeneous mixing kind of network, where you're only connected with some people, and that represents just your friends or your family. And then you can see how a disease could potentially be eliminated in the, here you have time 1, and by time 2, the disease is eliminated because you're not connected with everybody. And so, so if we want to add these different heterogeneities and complexities to models, then you can start building different differential equations and systems that have a lot of different compartments. And so here I'm just showing you how you would probably incorporate behavior change in an SIR type model. And so imagine that then you break the population into two kind of communities. And so there's one type of community that changes their behavior because there is a disease spreading in their community. And so then they decide to stay home or reduce the number of contacts or wear a face mask. And so they have their transmission rate is going to be lowered for that community that is actually changing their behavior. And then in the bottom is people that decide not to change their behavior, and so they go about their business just as if nothing was happening. And so then you can see then you have more complicated differential equations. And I have built systems where you have like representations of counties, and within each county you can have different age groups, and you can also have different types of communities or different schools or different workplaces. And so you can have like hundreds and hundreds of differential equations to kind of help you have more realistic dynamics in your model. And so when you add these types of complexities to your model, then you start generating more accurate results. And so here I'm kind of showing you the results of some of our models that have behavior change. And so on the left, I'm showing you what happens if no one changes their behavior. And then what happens if people change their behavior, only 15% of the population or only 30% of the population change their behavior. And then in the third row, it's like what happens if 50% of the population change their behavior. Then you start generating waves of infection. And this is something that we saw during the pandemic, because you have people kind of changing their behavior. And then once the disease seems to be going down, then they go back to now wearing face masks or having lots of contacts. And so then you see a rebound in the number of cases. And so you can get more complicated dynamics once you start adding more compartments to your models. And so this is one way that we simulate infectious diseases, but we also have more sophisticated ways of simulating infectious diseases. And this was mentioned in the clip that I played at the beginning. And so we've also have very large computer simulations. And a simple way to kind of think about this is video games. And so if you play video games like SimCity or some others, you can see how they have very complex terrains and people making different decisions. And so we also have similar capabilities where we have people across the United States. So we have about over 300 million people. And we have different communities, we have schools, we have workplaces, we have airports. And so then we can explore the impact of different mitigation strategies. And so what happens if we close schools? What happens if people start wearing face masks? What happens if people get vaccinated? And we can use that information to provide decision support to decision makers. We use lots of different data. And so here I'm just listing some of the data sources that we use. And so when you do this, so this is one of the simulations that we made during the pandemic. You can basically see the spread of an infectious disease or a pathogen across the United States. And then figure out what areas need more resources or more educational campaigns to help them reduce the potential impact of the spread. So here I've been talking about some of the work that we've been doing as it relates to infectious disease modeling and assessing the impact of different mitigation strategies. But other area that I'm really interested in and my team is working on is on forecasting. And so we've been inspired by the weather forecasting community, and many of you, have probably checked your weather apps every morning to see what you're going to be wearing or whether you need to bring an umbrella or not. And in a very simple terms, the way the weather forecasting community works is, they have observations from many, many different sources. They have like satellites that are kind of quantifying and measuring different things from temperature, precipitation. They also have sensors all over the world capturing different things that helps them forecast the weather. And then they have these sophisticated physics-based models to ultimately provide us with probabilistic forecasts of hurricanes or just the weather. And so we were inspired by this kind of approach and decided to see if we could actually apply them to epidemics. So that, you could also take many different data sources from social media, maybe satellite imagery, temperature, and many other data sources, combine them with mathematical models to ultimately give you a probabilistic forecast of how disease is going to spread in a community. And I think if we were able to accurately forecast infectious diseases, we could also reduce their impact, just like now, because we're able to forecast how when hurricanes are going to make landfall, you're able to evacuate people. If we know that an infectious disease is increasing in a community, we can inform the community and they can take the necessary measures to reduce the probability of infection. And so we've been working a lot on real-time disease forecasting, and the major problem with forecasting is the way we collect data for infectious diseases. And so I just wanted to kind of show you how a lot of the data is collected. So basically you have hospitals, you have laboratories, you have pharmacies. They have information about patients that are going in because they have a flu or they have COVID or they have other infectious diseases. They collect this data, and so then they provide it to probably the state Department of Health, and then eventually that information gets provided to the CDC, and then the CDC publishes the data to publicly for modeling communities like myself to use that data and see if we can use the data to forecast infectious diseases. The problem is that this process takes at least 2 weeks, and that's in the United States. But when we're collecting data from other countries, sometimes it can take up to like a month or 2 months to collect data. And so imagine how accurate the weather forecasting community would be if they could only collect data from like 2 weeks ago. So, I mean, it's hard already to accurately forecast the weather and forecast other things. But if you're not getting real-time data, it's even harder. And so, one thing that we decided to do in order to fill the gap, because we're not getting data on a regular real-time basis and on a daily basis, we get data every kind of Friday. For flu, we get data every Friday. And the data that we get on Friday is from 2 weeks ago, and so that's what happens. So we decided to see if we could use internet data to help us fill this gap. And the reason why we thought internet data might be useful is because a lot of people are using the internet to self-diagnose. So if you have sore throat or a fever or some rash, you typically go online and try to find information about your condition, and then also you may be able to find symptoms. I mean, if your symptoms are consistent with the disease that you're looking for, and then you also find treatments. So we started doing a lot of work on how we could use different data streams to help us bridge this gap. And one of the earlier kind of studies that we did was trying to use Wikipedia to track disease incidence. And so, everybody uses Wikipedia. They have, billions of articles across many different languages. It's one of the most popular websites. And the key piece is all the data is freely available on an hourly basis. And so we can see how many people are looking up influenza or dengue or HIV or any other, or COVID. And so we started looking at the traffic going to different articles related to different infectious diseases. And so here I'm just showing you the influenza page. And then also if people were clicking on different linked articles, such as symptoms or treatments or more information about influenza, we gather the traffic to all of those linked articles. And what we found was that actually internet search behavior correlates with disease incidence. We did this study we looked at articles about dengue in Portuguese in Brazil, flu in Poland, so the articles were in Portuguese, flu in the United States, tuberculosis in China, and then we found that just as the number of cases are being reported, and here the number of cases is shown in blue, and then in gray I'm showing all the Wikipedia articles that are related to this disease of interest, and then in red I'm showing a model that we built that uses the Wikipedia data to model, dengue or flu or influenza or tuberculosis. And so you can see that by using the Wikipedia articles, we are able to pretty much match the official surveillance data. And so therefore, this gave us additional data that we can use in our models. If we want to forecast dengue in Brazil, we can use the surveillance data that are being provided by the Ministries of Health. But in addition to that, we can also use Wikipedia data or Google Health Trends or many other internet data streams. And here I'm showing you a comparison between two different models that we built. The model on the top is just it's a model that doesn't have any internet data, and so all the black circles show the cases that are being reported for influenza-like illness in the United States. And then the solid line shows our forecast, and then the gray area is our uncertainty, and then in the open circle show what actually happened. But we pretended that we didn't really know what actually happened, and so we did our model using data up to a certain week, the week with only with the solid circles. And so then we were able to, in the second model, the bottom model, we used Wikipedia data. So we had all the reported cases, then plus Wikipedia data to fill out 2 weeks of data that we didn't have from the Departments of Health. And we were able to not only increase the accuracy of our forecast, because you can see that now our forecast is almost on top of the open circles, but you can also reduce the uncertainty, because in the top figure, you have like a lot of uncertainty, and then the bottom one, it's kind of converging towards what actually happened. And so we have been trying to figure out different ways to increase the accuracy and find ways to get more data so that we can forecast infectious diseases. And then I also wanted to kind of quickly show you how we can also forecast dengue, for example. We also have been exploiting different data streams. The reason why we have to exploit more data streams and not just internet data for dengue is because dengue is a mosquito-borne disease. And so ideally, if you want to forecast dengue, you would need to know where the mosquitoes are. So you would want to have like maps of mosquitoes. And if you know where people are, then you can kind of find a way to estimate the likelihood that a person can get bitten by a mosquito. However, there's no scalable kind of surveillance systems for mosquitoes, just because mosquitoes are very small and a lot, and it would be very hard to kind of collect information in very large areas, such as Brazil, for example. Imagine in the Amazon, I mean, it would be almost impossible to kind of have traps in many different places and then collect those traps and then figure out what kind of mosquitoes are spreading in those areas. So in order to mitigate that problem, we decided to start looking at satellite imagery. And satellite imagery can provide information about vegetation or water content in leaves or burn areas. And the reason why vegetation is important is because if the vegetation is green, then that means that there's been precipitation. And if there's precipitation, then there's a very good chance that there's mosquitoes in that region. And the reason why precipitation is really important for mosquitoes is because mosquitoes lay their eggs in standing water. And so the water is very important for their reproduction. And so we were looking at, obviously, areas that are very green are going to have a lot of greater chance of having mosquitoes. However, areas that have experienced wildfires, for example, are probably not going to have as many mosquitoes. And so that's why recognizing burn areas was important. We also use a lot of weather stations within Brazil because temperature is really important. Mosquitoes like to a certain temperature. They can't, if it's too cold, they die. And so temperature is important. We also gather a lot of demographic data from the census in Brazil, and they have a lot of different information about rural populations, about access to sewage, poverty, garbage collection, and many different things. And then we also, this time we decided to look at Google queries. And so people searching for dengue in Portuguese or dengue symptoms or mosquitoes or different types of mosquitoes, we track that for various cities. And so we apply different regression and statistical type models. And here I'm kind of just listing the different models that we applied. And here on the right, I have basically a figure showing you all the states in Brazil. There are 27 states, and I know it's very hard to see the names. And then on the y-axis, I'm showing you the results of each of the different models. If the darker the cell, the better the model. And that means there's less error in your predictions. And the lighter the cells, the more error you have in your predictions. And so what basically the take-home message of this figure and this analysis was that one size doesn't fit all. And this is really important for me as a mathematician, because typically we just build one model and then we're trying to make assessments about, different outcomes. But what these results are telling us is that, for some states, Sarima PCA is the best model, but for some other states, STL is providing you better forecasts. And so I think kind of trying different models, it's probably ideal for having more accurate results. And then here also I'm just showing you different predictions at the municipality level. So there's 5,570 municipalities, and then at the state level. And so you can see that by using different data streams and accounting for the environmental kind of conditions, you are able to better predict mosquito-borne diseases in Brazil. And then one other thing that I kind of wanted to mention is the contribution of the different data streams on the predictions. Sometimes we feel like putting more data is going to give us better results. And so we wanted to quantify the value of these different data streams because we are using a lot of data in our models. And so do we really need all this data, or do we maybe just need to focus on the cases, and the cases enough would be able to help us forecast? And so, so here you can also once again see that one size doesn't fit all. There are some regions and some states that need a lot more data because maybe the cases are not being reported because they have poor health infrastructure. Some areas needed satellite imagery and Google. Some needed like the weather, and some only needed the cases. And by none, I mean just clinical surveillance cases. And that enough would help you predict the cases for the next few weeks. And so we are trying to apply all these different tools and trying to exploit different data streams to help us forecast infectious diseases. And then one last thing that I wanted to mention, and this one is kind of very short, is about COVID-19 forecasting, just because obviously COVID-19 has been very present in our lives for the last few years. And so we've also were part of the CDC COVID-19 forecasting project. And at Los Alamos, we have a team that put out forecasts starting on April 2020 and through September 2021. We are no longer publishing forecasts, but on twice a week, we were providing forecasts, and we provided forecasts at the state level and also for 200 countries and territories. And the approaches that I've been discussing are very similar to what we use for this type of project. And so basically we were trying to forecast short term, which is 7-day cumulative confirmed cases, and then in deaths, and also 6 weeks. And so here you can see some of the forecasts that we were providing on a twice a week. And another thing that I also like to mention about our COVID work was that we also provided on with every forecast, we provided model performance. And so basically we went back and saw how well our forecasts were against what actually happened. And so we thought that was super important, because if decision makers were going to be using our forecast to determine how many beds they needed in certain regions, or resources, or educational campaigns, they needed to have confidence in our forecast. And so making sure that you are developing models that accurately forecast cases or deaths was super important. And I know I saw a lot of forecasts during the pandemic, but I didn't see a lot of people kind of actually showing how well their forecasts were. And so with that, this is some of the conclusions from my presentation. Basically, mathematical modeling has played a key role in helping us understand forecasts and response to infectious diseases, not just recently, but it's been ongoing for many, many years, as I showed you at the beginning during the history of mathematical modeling. However, epidemic forecasting is very new, but it's a growing field with great potential. I feel like the epi forecasting community is where the weather community was maybe 30 years ago. So we still have a lot to do. And I do think that the pandemic catapulted us forward, but we have to figure out how to exploit different data streams, because the current surveillance systems are not really set to have these real-time forecasting models. I also mentioned that there is value in adding heterogeneous data streams to complement clinical surveillance data, just because our clinical surveillance system typically provides delayed data, and so that is very difficult. The challenges, obviously, that we currently have in the epidemic modeling community is data availability. We also don't really have surveillance systems for how people change their behavior. And so while there have been surveys asking people, are you wearing a face mask? Are you staying home? Do you wear mosquito repellent? We don't really have a very centralized and consistent system that is collecting that kind of information. And that information is critical for developing accurate forecasts, because if people change their behavior, they can change your forecast. Obviously, also virus evolution, we've seen a lot of variants emerging, and so that is something that we need to take into consideration in our models. And then also going back to the uncertainty, capturing the uncertainties associated with the different data streams is crucial. And especially because each data stream is going to have its own bias, how it's collected. If we're using internet data, only certain populations are using internet data, and so we're not really capturing the impact in certain populations, right? And so figuring out how to exploit other data streams to help us address those biases is super, super important. And finally, I want to thank my team and many people that are helping with this work. And so obviously I'm just here talking, and everybody that's in this picture have contributed to different parts of our work. And so thank you very much.
Thank you for joining us. I know our participants are looking forward to live Q&A with you during the Institute this summer. Thank you all for watching. For more information on SICSS-Howard Mathematica, visit our website, follow us on social media, and join our email list.